All right, let's dive right into this explainer. Today, we're going to explore the high-tech ecosystem of an electric vehicle by following the fascinating journey of a single electron. Seriously, if you've ever wondered exactly how plugging a cable into your garage wall translates into blowing past sports cars on the highway, you are in the perfect place. We're going to break down the sheer engineering brilliance hiding just beneath the floorboards.
No, an EV isn't just a traditional car with a gas tank ripped out. It's a remarkably sophisticated, highly efficient electronic ecosystem. When you strip away the outer shell, you realize the bulky internal combustion engine, the incredibly complex multi-speed transmission, the exhaust pipes, they're all completely gone. In their place is this streamlined, elegant network of batteries, converters, and motors. It's a fundamental reimagining of mobility, shifting us away from mechanical complexity and straight into electrical efficiency.
So here is our roadmap for today. 1. Powering up, AC versus DC. 2. The battery management system. 3. The inverter, DC to AC. 4. Motors, induction versus permanent. And finally, 5. Regenerative braking, recovering energy.
Let's kick things off with Section 1, Powering Up, AC versus DC.
Think of your EV's battery like a massive water tank. AC home charging? Well, that's like using a narrow funnel, which obviously limits the flow. But DC fast charging out on the highway, that acts like a fire hose, pumping power straight in. Here's the deal. Your EV's battery can strictly only store energy as direct current, or DC. But the power grid at your house delivers alternating current, or AC. So when you plug in at home, that AC power has to be converted first. That conversion is your bottleneck. It's your funnel. DC fast chargers, on the other hand, handle that massive conversion externally at the charging station, which totally bypasses the car's internal limits.
The key player in this whole conversion process is a piece of hardware called the onboard charger, or OBC. This is your AC funnel. It takes that grid alternating current and magically converts it into direct current so it can be safely stored in the vault. And here's why that matters. Even if you plug your car into a super high-powered AC wall box, if your car's OBC is only rated for, say, 11 kilowatts, it will simply refuse to pull more than that. This little hidden component entirely dictates how fast you can charge in your garage overnight.
Moving right along to Section 2, the battery management system. Now we meet the absolute unsung hero of the EV, the battery management system. Because let's be real, you can't just dump raw electricity into hundreds of individual lithium-ion cells and hope for the best. The BMS is the absolute brains of the battery pack. It is constantly, relentlessly monitoring the voltage, the current, and the temperature of every single cell in real time. The crucial takeaway here is that the BMS actively protects the battery. It manages extreme temperatures, prevents overcharging, and tracks the electron flow like a high-tech fuel gauge. And thermal management, it is absolutely vital. Think of lithium-ion cells as total divas. If the battery is too cold, it charges sluggishly. If it gets too hot, it degrades rapidly and can even become a severe safety risk. The BMS steps in to perfectly balance the load across all those cells so they drain and fill evenly. That ensures you get the absolute maximum lifespan and driving range out of your car.
Section 3, the inverter, DC to AC.
Enter the inverter. This critical device is your translator. It takes that flat, incredibly stable DC battery juice and transforms it into the variable AC power required to actually physically drive the car. Without the inverter, all that stored energy is just trapped. The inverter takes the direct current and rapidly switches it back and forth, creating an alternating current waveform that the traction motor can actually use to generate a rotating magnetic field.
By converting the current this way, the inverter gains the superpower to precisely control the speed of the motor and the torque it produces. It doesn't just flip a switch on and off. It modulates the frequency and the amplitude of that AC power hundreds of times per second. Think of it as the ultimate conductor of an electrical orchestra. When you mash the accelerator pedal, you aren't opening a valve. You are actually just telling the inverter to change the AC frequency, which instantly spins the motor faster.
All right, Section 4, Motors, Induction versus Permanent.
This right here is the climax of our electron's journey. This is the exact moment where electrical energy is finally converted into mechanical kinetic energy. There's no combustion, no tiny explosions pushing metal pistons up and down, just pure, silent electromagnetism. A magnetic field generated in the stationary part of the motor, called the stator, literally drags the spinning part, the rotor, along with it. But exactly how that rotor is designed? Well, that brings us to a massive engineering divide in the EV world.
When we compare the two main types, AC induction motors are super rugged and can actually freewheel without any drag. Meanwhile, permanent magnet motors use rare earth metals to achieve just incredible power-to-weight ratios. See, in an induction motor, the electrical current actually has to be induced into the rotor to create a magnetic field. That requires a little bit of extra energy and a tiny bit of slip, but in a permanent magnet, or PM motor, the rotor already has super strong rare earth magnets built right into it. The magnetic field is just always there, waiting to sync perfectly with the stator.
And because of that setup, permanent magnet motors hit an astonishing 95 to 97% peak efficiency. Virtually all modern EV manufacturers have adopted PM motors to maximize how far you can drive on a single charge. Since they don't waste precious battery power inducing a magnetic field in the rotor, they are remarkably efficient, especially when you're varying your speeds. This is exactly why companies like Tesla shifted heavily to PM motors for cars like the Model 3. That extra efficiency directly translates to saving battery capacity and extending your range. Though, here's a fun fact, some all-wheel drive EVs will actually still use an induction motor on one of the axles. Why? Because unlike a PM motor, an induction motor can be fully de-energized. It can literally freewheel with zero magnetic drag when you're just cruising on the highway.
Finally, Section 5, Regenerative Braking, Recovering Energy.
The sheer brilliance of electric vehicles is that the journey doesn't end at the wheels. Through regenerative braking, when you simply lift your foot off the pedal, the motor reverses its role and becomes a generator, clawing back that kinetic energy and sending it right back into the battery. Think about a traditional gas car. When you step on the brakes, all your forward momentum is violently converted into useless heat by the brake pads. It is totally wasted energy. But in an EV, the wheels actually physically backdrive the motor. The whole system just flips. The mechanical energy of the moving car generates alternating current, the inverter flips it back to DC, and the battery captures it. It is literally free energy recovery just from slowing down.
Summarizing this entire closed-loop ecosystem, the journey of energy is remarkably elegant. The grid feeds the battery charger, which safely fills the battery under the incredibly watchful eye of the BMS. Then, the inverter translates that power for the high-efficiency motor to drive the transmission. And thanks to regenerative braking, the flow literally reverses, pushing power back against the current to recharge the system. It is an incredibly sophisticated, low-waste machine.
So, I want to leave you with this final thought. If this closed-loop technology is already this incredibly efficient, how will this high-tech ecosystem possibly evolve next? We are already squeezing 97% efficiency out of these motors, so the next frontiers? They'll likely be found in breakthrough battery chemistries, even faster charging architectures, or perhaps completely rethinking how we manage thermal energy altogether. Thank you so much for joining me on this explainer today, and keep questioning how the world around you is powered.